In today's class, we will see what is a Poynting theorem. And so Poynting theorem is actually concerned about the flow of electromagnetic waves and what is the power involved. You know that electromagnetic wave, which is a combination of electric and magnetic field, when it is flowing, there will be some sort of power involved in that. So Poynting's theorem helps you in calculating that power. So first of all, we will understand how the power is flowing in electromagnetic wave. So what is the concept there? Then we will realize what is a Poynting vector. And then finally, we will state what is a Poynting theorem. Okay. So now let's see. We know that electromagnetic waves or EM waves, it carry electric power with them. Electromagnetic waves carry with them electromagnetic power. So when electromagnetic power is being carried, energy is being transported through space. So you know that energy is being transported through space during electromagnetic wave propagation. So for you to write notes only, I am writing all these things here. Okay, so electromagnetic waves carry power along with them, electromagnetic power. So there will be an energy being dissipated. So while the wave propagates, energy is being carried. So what we need to do, we need to find a relation between the rate of such, that is the rate at which such energy is being transferred, and the electric and magnetic. So you know the electromagnetic wave will be a combination of electric and magnetic field. So we need to find a relationship between the rate at which this energy is being transferred and the electric and magnetic field. So that's what our aim. So relation between rate at which energy is transferred and electric and magnetic field. So that will be the main area of concern of. So that will be Poynting theorem. So once we find out this relationship, that will be Poynting's theorem. So if in order to find out that, we are using our same Maxwell's equations. So we'll use this equation: del cross E is equal to minus dou B by dou T. We'll keep that as equation 1. And we'll use the other equation also, del cross H, which is equal to J plus dou D by dou T. So this is equation 2. So what we are trying to do, we know the electromagnetic waves, a combination of electric and magnetic field. So now we are on to a topic where we are studying about the power being transferred or the energy being transferred. So now we are going to find out a relationship between the energy being transferred as well as the electric and magnetic field. And for that, we are using the Maxwell's equation. Okay, now we have a term, we know E cross H. So we have a term, electric and magnetic field, the curl. So now we will take the divergence of E cross H. Taking divergence of E cross H. So when we take the divergence of E cross H, it will be del dot E cross H is equal to H dot del cross E minus E dot del cross H. So this is actually identity that we have studied in our basics, module 1. Del dot A cross B is equal to B dot del cross A minus A dot del cross B. So we have used this particular identity here. So now what we do, we have equation 1 and 2. So the terms from equation 1 and 2, del cross E, we have one expression, del cross H, we have one expression. So that we will substitute here. Put 1 and 2 in 3. Then our equation is updated to del dot E cross H is equal to H dot. So del cross E is minus dou B by dou T minus E cross, and del cross H is J plus dou D by dou T. So now again you know that B is equal to mu H as well as D is equal to epsilon E. Then our equation gets updated to, so I'm not writing the left hand side. So our RHS will be equal to, so left hand side will be same. So our RHS will be equal to H dot minus dou by dou T of B is mu H, right? So mu H minus E dot J minus E dot dou by dou T of D is epsilon E. So I think all these steps will be very much clear for you. So epsilon E, so that is equation number 4. Okay, so now when we come to a simple medium, in a simple medium, epsilon, mu and sigma do not change with time. So we have seen that in our earlier studies. Therefore, we can write. So now what we will do, so we have 3 terms here, right? So the RHS is 3 terms here. So this is the first term. So I will use 3 different colors to make it clear for you. So this is the second term, and this is the same color only. So this is the third term, right? So now we will take all these 3 terms separately. First term, second term, and third term. So all these terms will take separately, and then we will find out whether we are able to find a energy related relationship. That is del dot E cross H should be equal to some energy, right? So that we are talking about the energy being transferred, and let's see whether we can bring in some energy term in all this by analyzing this. So moving ahead, so I will take the first term. The first term is H naught minus dou by dou T of mu H. So that can be written as minus mu H dot dou H by dou T. So that is equal to, I will tell you how it is coming, minus mu into dou by dou T of H dot H. So that you just try the reverse from here, because I think you might have doubt how the step came. So I will just show you. Half into, so mu and all it's constant, same mu only. So how this 1 by 2 came, I am just showing it. Half into dou by dot T of H dot H. So that is equal to 1 by 2 into dou H by dou T into H. And that is plus 1 by 2 into H dot dou H by dou T, and that again is equal to H dot dou H by dou T, and H dot H can be written as H square. So this same property is being used here. So this is updated to minus 1 by 2 mu dou by dou T of H square is equal to minus dou by dou T of 1 by 2 into mu H square. So we have reached this expression 1 by 2 into mu H square. So let it be there. We will talk about that later. Now we will take the third term. So second term is little more simple. Now we'll take the third term underlined in orange color. Third term, and then we will see the same way we will analyze that also. That is E dot dou by dot T of epsilon E is equal to epsilon E dot dou E by dou T, that is equal to the same property we will use, half into epsilon into dou by dot T of E dot E. So that is getting updated to, so half into, so at least some of you might have understood what we are doing. So you know this equation, energy stored is half epsilon into E square. We have studied in, for electrostatic, we have studied in module 2, energy is half epsilon E square. So now we have brought in the energy term, right? So dou by dou T of half epsilon square, and in terms of magnetic field, it is dou by dou T of 1 by 2 mu H square, same thing. There it is permeability, and here like that their dielectric medium change only is happening. And now we will analyze the second term. So second term, what does that say? E dot J. So E dot J we can write E dot sigma E, which is equal to sigma into E dot E, that is equal to sigma E square. Now the same old equation, the equation number 4, here we will update with the new values. So the equation number 4 will update with the new values, and we will get it like equation 4 becomes del dot E cross H is equal to minus dou by dou T of half into mu into H square minus second term was sigma E square minus dou by dou T of half into epsilon into E square. Okay, so now this is a dou by dou T terms we can take common. So what is it? What does that become? So it will be, I will write the LHS also here, del dot E cross H is equal to minus dou by dot T of half into epsilon E square plus half into mu H square minus sigma E square. So this is actually a point function relationship. So now we will integrate. So this is a particular, but this is actually at a particular point. Now we will integrate this over a volume. Integrating over a volume. What you will get? Integral over V del dot E cross H dV is equal to minus dou by dou T of V half epsilon E square plus half into mu into H square into dV minus integral over V sigma E square. So on the RHS we have all energy terms only. So sigma is the energy dissipated, that will see, I will tell you. So now we will apply divergence theorem. by applying, so you know integral over V del dot E cross H by applying divergence theorem, we can write integral over S E cross H ds is equal to minus dou by dot T of integral over V half into epsilon into E square plus half into mu into H square into dV minus integral over V sigma E square dV. So now what we have arrived? We have two different terms, right? Listen carefully. We have half epsilon E square as well as we have minus half mu square. So this minus is common for both of them. Okay, don't mistake in that. So common for the other, and then we have minus sigma E square. So this is our equation number 5. So now the statement which I am going to say is very important. The first two terms, so we have two terms here in the right hand side, it shows the rate of change of energy stored in electric and magnetic field, right? Half epsilon E square and half mu square, and they're changing with respect to time. So dou by dot T of the first term, that is first two terms, it actually shows the first two terms. The first two terms in equation 5 shows the rate of change of energy stored in electric and magnetic field. I'm using the simple. And third term, you know, sigma and all, it is involved in conduction, right? So it is the ohmic power dissipated. The third term is the ohmic power dissipated. So now we find out RHS. So what is actually the RHS? They are all concerned with energy and power. So RHS of equation 5 is the rate of decrease. So why I am saying decrease? Because both the terms, all the three terms have a negative sign. So we can conclude. So this is our conclusion, or this is our finding. RHS of equation number 5 is rate of decrease. So why decrease? Due to the negative sign of electric and magnetic energy stored as well as subtracted by the ohmic power, comma, subtracted by the ohmic power. So ohmic power, you know, it will be normally dissipated as heat. So in your power electronics class, you will study about inductor, capacitor and all, how they store energy. So ohmic power is dissipated as heat in volume V. So over the volume V, which we have integrated, right? So now we found out RHS. So what does law of conservation of energy say? The law of conservation of energy says that this change, this RHS, this should be equal to the power leaving the volume throughout its surface, right? By law of conservation of energy, this, that is the RHS side, must be equal to the power, that is rate of energy leaving the volume through its surface. By law of conservation of energy, by law of conservation of energy, this must be equal to the power. Power is actually rate of energy, right? So rate of energy leaving the volume. Through its surface. So rate of energy leaving the volume through its surface. So what does the LHS become? Then LHS, which is actually E cross H, is a vector representing the power flow per unit area. So we can write P is equal to E cross H. So this is actually your Poynting's theorem. So we will reach there, but still I am saying this Poynting theorem, where P is a Poynting vector. So P is a, I think I is not there, Poynting vector. So P is a Poynting vector. So a question comes, then you should write all these stories. Which is a power density vector? Poynting vector, which is a power density vector. P is a Poynting vector, which is a power density vector associated with the electromagnetic field. So now we will just conclude. So what is our finding? Integral over S, closed integral over S, E cross H ds is equal to minus dou by dou t of integral over V half into epsilon E square plus half into mu H square, plus because I have taken minus common outside, dV. So I'll keep this in a bracket, dV minus integral over V sigma E square dV. So what are the individual terms here? This is the total power leaving the volume. Total power leaving the volume, and this is the rate of decrease of energy stored in electric and magnetic field. So this is the rate of decrease of energy stored in electric and magnetic field, and this is the ohmic power dissipation. Ohmic power dissipation. So this is the main essence of Poynting's theorem. So now we will define Poynting's theorem also. So before that, let me see. So now we will define what is Poynting's theorem. Poynting's theorem states that the net power flowing out of a given volume V is equal to the time rate of decrease in the energy stored within V minus the conduction losses. The same thing which we have written equation wise. So all you write all these stories, then you will get full marks. So you should understand. Don't never by heart anything. You should understand. So what all things we can write from here? We can write P is equal to E cross H. So this is the basic statement. That is, now we need to find the direction. The direction of Poynting vector P is normal to both E and H and is therefore along the direction of wave propagation AK for uniform plane waves. Where AK is equal to, so you have mutually perpendicular, right? So where AK is equal to AE cross H. So E cross H, then the unit vector also same way. So the P here is known as, P is specifically known as instantaneous pointing vector. Okay, so bit more is there, I'll just complete. So complex pointing vector is, so complex pointing vector will be P is equal to half into, you know what is ES? We have already studied. ES is the phasor form. Phasor form of E, and HS star is the complex conjugate of phasor form. So about phasor form, you have an idea. We removed the T domain and we already seen. So therefore, average pointing vector P average is equal to 1 by T integral 0 to T P dt, which is, so you know, when we study phasor representation, we take the real part, like, so P average is equal to 1 by 2 into real part of ES into HS conjugate. So this concludes our Poynting's theorem. So there is one more numerical problem is also there. That also I will teach you. So this is how. So now we have. So what we have done, we have understood that electromagnetic waves, there is a power flow also. Then we understood the rate at which this power is flowing. Then we realized that it is equal to this much term. This is the power, that pointing vector P is equal to E cross H. Then we state the Poynting's theorem, and also found, and also we understood the direction of the pointing vector. Okay, and then we found out the average pointing vector also by using the phasor concept. So just this equation you can understand. And if at all they ask you in phasor form, then you can write these things. That's it. Now we will solve a numerical problem based on this question. So here, based on this topic. So what they're asking is, show that the power flow along a coaxial cable. So you know a coaxial cable is the product of voltage and current. So we have a voltage here and current here, and our resistance, load resistance is also given. So we need to show that the product of the current flowing as well as the voltage by using, so power flow is the product of voltage and current using Poynting's theorem. So we need to prove that. So we'll consider the radius of the inner conductor is equal to A. Let radius of inner conductor. So this is an example question given in Sadiku, and let the radius of outer conductor is equal to 2b. If you see, you can understand it is 2b, and here the radius is A. Let the voltage, between the conductors be V, and a steady current flows as shown in figure. The magnetic field intensity at a distance r from the center of inner conductor is H is equal to I divided by 2 pi r. So this we have obtained from the Ampere's theorem. Therefore, so this is magnetic field intensity of a coaxial cable. Therefore, electric field intensity at a distance r from center of inner conductor is equal to rho L by 2 pi epsilon r, where rho L is the charge per unit length. So rho L is the charge per unit length. So now now we will study the potential difference. Potential difference between inner and outer conductor is V is equal to minus integral B to A E dot dl minus integral B to A rho L by 2 pi epsilon r dr is equal to minus, so now it's just mathematics only, 2 pi epsilon into log r to the base e B to A is equal to rho L by 2 pi epsilon into ln B by A. Right? Then we can write V is equal to rho L by 2 pi epsilon into ln B by A is equal to rho L by 2 pi epsilon r. So we will multiply and divide by r. Why? Because we need to bring in the electric field term, electric field L into ln into B by A into r. Then we can write E is equal to V by r into ln B by A. So what does that mean? The total power flow along the cable. So now we have a statement. The total power flow along the cable can be obtained by integrating the Poynting vector over any cross-sectional area 2 pi r into dr. Therefore, total power flow is equal to integral over S P dot ds is equal to integral over S E cross H ds is equal to integral EH ds is equal to integral V by R into ln B by A into I by 2 pi R into 2 pi R into dr. Okay. So that will be Vi by ln B by A integral A to B dr by R, that is equal to Vi by ln B by A into ln R A to B. I'll finish it here itself. A to B. So that is equal to, so you can understand that this 2 will get cancelled, right? So Vi by ln B by A into ln B by A is equal to Vi. So we have proved that the total power flow is equal to V into I. So that's what they were asking us, right? So this is how we should solve it. So what we have done, we have shown that the power flow along a coaxial cable is the product of voltage and current using Poynting's theorem. Thank you.